everyone, welcome back to The Explainer. If you're a mechanical engineer, you already know the universal truth of our profession. Heat is literally the enemy of efficiency. Today, we're unpacking a really fascinating technical briefing on floating photovoltaic systems, or FPVs. Placing solar panels on water already gives us a nice thermal advantage over land, but as global installations scale up rapidly, we're all hunting for ways to extract even more heat and squeeze out every possible watt. So let's dive into the cutting-edge thermal management strategies designed to cool floating solar modules.
All right, here's our roadmap for today. We'll start with the FPV Thermal Management Challenge, then look at active cooling configurations, followed by passive cooling configurations. After that, we'll cover climate and hydrodynamic impacts, dig into the techno-economic performance metrics, and finally wrap up with technology readiness levels.
Let's kick things off with Section 1, the FPV Thermal Management Challenge, or basically our thermodynamic problem.
So, an efficiency drop of 0.5%? That is absolutely the villain of our story here. For every single degree Celsius increase in a PV cell's operating temperature, its electrical efficiency drops by an average of 0.5%. And when you've got a massive floating solar array just baking under the midday sun, panel temperatures can easily soar past 60 degrees Celsius. That kind of thermal stress doesn't just throttle your power output, it actually accelerates material degradation, which shortens the lifespan of the entire system. Bottom line, we have got to get that heat out.
But look, as engineers, we can't just look at raw cooling power, right? We have to evaluate the system as a whole. And that brings us to our baseline metric for today, net electrical efficiency gain. This is the effective improvement in electrical power output after subtracting any parasitic energy consumed by auxiliary systems, like pumps or fans. The crucial point here is that if you build a massive pumping system to cool your panels, well, you have to power that pump. That's your parasitic load. The net gain is exactly what's left over after you've paid that energy toll. Definitely keep this definition in mind, because it's absolutely going to make or break the technologies we look at today.
Moving on to Section 2, active cooling configurations, specifically focusing on forced convection. Let's consider the architecture of an internal pumped water cooling system. What we've got is a lightweight serpentine cooling block attached directly to the back surface of the solar module. A low-cost pump actually pulls water from the reservoir below, usually about 6 meters down where it's noticeably cooler, and forces it through these 10-millimeter thick polypropylene channels. The thermal extraction happening here is, well, it's aggressive. Under peak solar irradiance, this setup can drop the panel temperature by a massive 36 degrees Celsius. It's a total brute force thermodynamic win, slashing the temperature by over 57%. But as we all know, brute force comes with trade-offs. The divide between active and passive cooling is pretty stark. Active systems give you that massive temperature drop, like we said, up to 36 degrees, but you're taking on that parasitic pumping power. Now sure, in well-designed systems, that pump might use less than 1% of the total output, which sounds great. But you're also adding moving parts, and we know that means higher maintenance over a 25-year lifespan. Passive systems, on the flip side, give you a smaller temperature drop, usually around 3 to 15 degrees, but they run on zero parasitic load and offer incredible long-term cost-effectiveness.
Which leads us right into Section 3, passive cooling configurations, relying on natural convection and conduction.
Now consider the natural convection cooling loop, or NCCL. Instead of a pump, this system relies entirely on buoyancy. You've got a reservoir tank positioned just slightly above the PV module. As the fluid behind the solar panel heats up, its density decreases, causing it to naturally rise up into the reservoir while the cooler fluid flows down to replace it. It's really an elegant, self-sustaining loop driven entirely by the very waste heat we're trying to get rid of. Let's quickly walk through the exact 4-step thermodynamic cycle happening here. Step 1. Heat conducts from the hot PV cell right through the rear surface. Step 2. The fluid inside these specific 14 by 14 millimeter square aluminum pipes absorbs that heat and expands. Step 3. Natural convection forces this lighter, hot fluid upward and into the tank. And finally, Step 4. The heat is released into the environment from the reservoir, the fluid cools down, becomes denser, and makes its return back to the bottom of the panel. Honestly, it's just a beautiful application of fluid mechanics. Another incredibly clever passive approach is the finned heat sink. Instead of an enclosed loop, U-shaped aluminum fins are attached to the back of the module and partially submerged directly into the lake or reservoir. Now, engineering this definitely requires some precision. The analysis shows that a submerged area ratio of 20% is the exact sweet spot. If you submerge them too deep, you might accidentally alter the angle of the panel and lose solar irradiance. But at exactly 20%, you completely optimize the balance, dropping the temperature by several degrees while actually boosting gross power output by over 16% compared to a standard, uncooled panel.
All right, on to Section 4, climate and hydrodynamic impacts, looking at those crucial boundary conditions.
Because, think about it, when you submerge a fin in a living body of water, the local hydrodynamics totally dictate your cooling capacity. The source material highlights several really specific variables to watch: a water current velocity of, say, 0.3 meters per second, a wind speed of 5 meters per second, and a flow incidence angle of 60 degrees. But honestly, perhaps the most fascinating variable is the actual geometry of the fin itself. Like, is it a solid sheet of metal, or is it perforated with holes? It turns out perforated fins actually disrupt boundary layers and significantly enhance thermal mixing under these specific flow conditions.
And the result of getting all those boundary conditions and geometries exactly right, a massive 22.8% net electrical efficiency bump. Yeah, you heard that right. This was achieved using those perforated fins under optimal wind and water current conditions. It just goes to show that if you design your passive system to really harmonize with the local hydrodynamics, you can achieve efficiency gains that totally rival active pumping systems, but with literally zero energy penalty. Let's shift gears to Section 5, Techno-Economic Performance Metrics, evaluating the LCOE. All right, let's synthesize the performance data and see what the economics look like. The active systems, like the water veil and internal pumped blocks, give us really solid, guaranteed net efficiency gains, somewhere between 6 and 11%. But because of the upfront capital costs of all those pumps and piping, their LCOE reduction is relatively modest, capping out around 5%. Now look at the passive systems. Because they have virtually zero maintenance and absolutely no parasitic load, that 22.8% efficiency gain from the perforated fins translates directly into a massive 17.7% reduction in LCOE. Plus, it cuts the payback period by almost a third. Economically speaking, passive design completely dominates here. Finally, Section 6, Technology Readiness Levels, Assessing Deployment Viability. To figure out how close these are to real-world deployment, the researchers used a really rigorous technology readiness level framework. So they aren't just looking at theoretical thermal models, they're actually scoring these systems based on the type of validation, the scale of the prototypes, whether they were tested in controlled labs versus real outdoor floating environments, and, critically, the availability of long-term operational data. What they found is that while some active systems are a bit closer to off-the-shelf readiness today, the passive systems are rapidly maturing through pilot-scale validations as we speak.
I want to leave you with this definitive takeaway directly from the source material. While active cooling methods offer superior thermal performance, passive systems present a more scalable and cost-effective solution for large-scale deployment. As engineers, it's always tempting to just brute force a thermal problem with a bigger pump and a huge heat exchanger. But as we look at deploying the next terawatt of floating solar across the globe, we really face a fundamental design choice. Do we accept the lifelong parasitic drag and maintenance of mechanical pumps? Or do we engineer solutions elegant enough to just let nature do the work for us? Thanks for joining me on this explainer. See you next time.